is especially useful.
In reflection seismology, what we try to do is generate that source or that shock wave ourselves and try to reflect that off of subsurface rocks and record it at the surface with geophones. We do that by sending out a truck into the field, which we have a truck called a Vibrasize truck that actually shakes the ground. A Vibrasize truck would shake the ground in an up and down fashion, much like a jackhammer on a construction site shakes the ground. And so what we're trying to do is use the technology so we can see the secrets of the earth below.
Because the shock waves interact differently with different kinds of rock, reflection seismology helps geophysicists find geologic structures that commonly contain oil and gas. Such structures can be detected not only by seismic techniques, but by observation from aircraft or satellite as well. This method of long-distance viewing is called remote sensing.
It's a way of looking at very large areas very quickly and getting an overview. Particularly since the advent of satellite remote sensing, we have had the luxury of being able to look at very large areas of the Earth's surface at one time and get an integrated idea of what's going on. What remote sensing has done, or satellite remote sensing particularly, has given us a chance to look at the interrelationship between widely separated features and see those in a way that we've not been able to see before.
In one recent investigation of the potential oil and gas reserves of Pakistan, 28 separate images were combined to form a mosaic which showed numerous spectacular geologic structures. Because of their remoteness, many had not been seen by ground-based geologists. This opened up new areas for oil and gas exploration. But remote sensing is by no means limited to the search for new sources of energy. It has also been used to study changing vegetation patterns, locate mineral deposits, track pollutants, and search for another critical resource, groundwater. The amount of water lying underground is vast, more than 30 times the total supply of water stored in all the world's lakes and rivers. Civilization depends heavily on groundwater, and as population rises, this resource becomes increasingly valuable.
The thing is that groundwater is almost always there, but it may be too deep to be economical to drill. It also may not be a good purity. Today we have severe problems with pollution, contamination, and groundwater, as we go deeper, gets older, gets hotter, and gets saltier. So you don't want to go real deep.
In the Southern California area, there are a number of factors that create a favorable environment for groundwater, including very permeable soils, a large storage capacity, and a steady supply of surface water. At the Orange County Water District, Jim Goodrich is responsible for managing the groundwater supply. He is concerned both with the quantity and the quality of available water.
So what we've done at Orange County is developed a very sophisticated groundwater monitoring program, which uses surface water sampling, production well sampling, and dedicated monitoring well sampling. Our monitoring wells are drilled to a depth of about 1,500 feet and isolate and tap up to 18 zones that we can monitor individually, so that if a contaminant is coming towards us, towards a production well, we can find it before it becomes a problem and institute a mitigation.
Like water, soil is a geological resource essential to sustaining civilization. For farmers like Wayne Soplan, who lives in California's Mojave Desert, maintaining a fertile, plentiful supply of soil is an ongoing struggle. The chief threat is erosion, which can be caused by either rain or wind.
Rain is a fairly minor situation here in the desert, We only have 4 inches of annual rainfall. Sometimes it all comes at one time, and we do have some runoff from sloping parcels or some stream bank erosion in streams that are normally dry. But that's relatively minimal. Our major problem with soil erosion results from the wind. And that can happen at any time of the year, winter, summer, fall, doesn't matter. And we have fairly heavy winds for long periods of time. And we have to take a number of precautions related to that.
To dissipate the strong winds that can remove a half inch or more of soil in a single day, Soapland has planted dense rows of trees known as windbreaks around his fields. He's also turned to the United States Department of Agriculture for additional ideas. After visiting Soapland's farm and learning about his primary concerns, soil conservationist Rick Aguayo drew up a soil management plan. This plan included suggestions about how frequently to plow the fields, as well as recommendations concerning water management and crop rotation. Along with the use of windbreaks, these soil conservation techniques are making a significant difference on Wayne Soapland's farm. These improvements are not just quick fixes, but substantial changes that will keep Soapland's soil productive for years to come. Whether the specific issue is soil, minerals, oil and gas, or water, there is a growing awareness that modern civilization is rapidly depleting Earth's supply of precious natural resources. And it is geologists who are devising new ways to more intelligently extract and conserve these resources. But their role extends well beyond the hunt for resources. Earth scientists are also deeply involved in helping the world's population safely coexist with this planet's many geologic hazards. One of the more serious hazards in terms of potential destruction is volcanic eruptions. And while there is no way to eliminate eruptions, scientists are continually refining their techniques for forecasting such events.
Probably all volcanic eruptions are preceded by and accompanied by measurable changes in the physical or chemical state of the volcano. And one of the principal means of monitoring or measuring the change, at least the physical configuration of the volcano, is by means of what we call ground deformation studies. And this simply is just a term for measuring the changes in the shape of the volcano.
In a research project underway in Alaska, geologists are studying one of the most powerful volcanic events of the 20th century, the 1912 eruption of Mount Katmai. Scientists there believe this is an excellent setting in which to learn more about how explosive eruptions occur.
It all happened in about 60 hours. We know exactly when, the date, the time. And also, which is also very unusual, is that it came up through an area where nothing much had happened volcanically